Welcome to another video. We have a crazy integral here that would require some extra steps in getting the answer. I'm actually doing this video in collaboration with my friend, Dr. PK Math. Please check out his channel. He's going to be solving this same integral using a completely different strategy. What I'm trying to do for this problem is solve it in a way that most people can relate to, because I'm going to be using the basic U substitution, integration by parts. I tried as much as I can to stay within those strategies, but I failed because this thing just requires one extra step. And unless your differential equations professor taught you the Fourier series, then it would not be completely strange. But I still had to use some Fourier series strategy to be able to compute the final answer. So what I'm going to do is start from the strangest part of this computation, and once I show you what happens at the end, we can go to the beginning and walk our way all the way to the end. Okay, let's get into the video. If you don't know anything about the Fourier sine series, but you're seeing it because I need to use it here, I promise you that in the next 1-2 weeks, you will be completely familiar with this, because I'm going to make a number of videos just to explain what happens here. Okay, so I need to show you where we're gonna go, and then we can start the work. But this is the very last piece of the puzzle. So every function, not every function, but almost every function can be expressed either as a sine series or a cosine series or a combination of both. And that's what you call the Fourier full series, the full Fourier series. Now, fortunately, we have something for this one. Okay, this is actually called the half range formula, okay, for this function. And what you have here basically is how you represent this function. So pi x minus x squared can be written this way, and you can compute the answer. If you compute on this side, it's the same thing you're going to get on this side. Okay, but it's easier to work with this because sines and cosines just tend to make our lives a lot easier. As long as you plug in anything, it can be evaluated, right? And things don't get too big or too small, because sine tends to keep things between -1 and 1. That's a good thing. Now, we're going to, at the end of the day, we're going to come back to use this formula to compute the value of the integral. Okay, so when you see me write this, don't be puzzled. Maybe we should do it now. Okay, so what we have at the end is going to look like this. Let me show you what happens at the end. We're going to have a sum that looks like this. N equals 0 to infinity. We're going to have -1 raised to power n. And at the bottom of it, we're going to have 2n plus 1 cubed. That's it. We just want to know what the value of this is. Now, it is impossible for you to understand fully what this is if you're trying to find the sum to infinity. Now, you imagine being asked to find the sum of these. What you can do, you may try the first, second, third. The first term will clearly be 1, because this will be 0. Anything raised to power 0 is 1. And down here, you're going to just have 1 cubed. So it's 1 over 1. So you're going to get 1. And as you can see, it is very difficult to find the total that we're going to get. But if you know a function that can give you something similar to this, and that's the function. That's why we chose this one. There are different functions, okay? Different functions, different ways these are written. So, because this is a trick that you need, it means you already know this function. That's why you're using it, okay? Now, because we already know this function, we can manipulate this part to look like this. Because the only thing different between this part here and what we have here is just that what you have here is sine 2n plus 1 x, but what you have is just -1 raised to power n. Remember, -1 raised to power n just means you'll always have +1 or -1. Okay, depending on what n is. That's why it's alternating. Once you go from one to the next, it changes from plus to minus to plus. So it's an alternating series. So it's clearly a convergent series, just based on what you know, okay, from your calculus 2. So here, what can we do to sine 2n plus 1x so that what we have there will always be minus 1 or plus 1? Firstly, you have to decide here, whenever you're dealing with sine, okay, this sine 0 is 0, right? Sine pi is 0. But when you get here, it is 1. Sine pi over 2 is 1, and sine 3 pi over 2 is negative 1. So the one that gives you the option, of whether you get plus or minus, it depends on whether your pi over 2 is here or your pi over 2 is here, right? So it can either be 1 pi over 2 or 3 pi over 2, odd numbers, and this is generally odd numbers. So this is a representation of odd numbers. So the only thing you were worried about is this x. If your x could be pi over 2, then at any point, this will be an odd pi over 2. It is either a 1 pi over 2 or a 3 pi over 2, which is plus or minus. And that's the trick in this. So what we're going to do is we're going to say our x is pi over 2, and that's it. That's the biggest problem in this problem. Okay, so let me get rid of this, and then we're going to choose our x to be pi over 2. But once we know that pi over 2 fits the bill, then it means this must be pi over 2, and this must be pi over 2, and we can transform this to be just negative 1 raised to power n, because that's what it means. So we're going to do this. We're going to say, let x be equal to pi over 2. Okay, then what do we have? We're going to have pi over 2 times pi minus pi over 2 will be equal to 8 over pi times this sum. The sum is from n equals 0 to infinity, but because we've chosen this to be pi over 2, the expression on top will become negative 1 over n, to the power n over 2n plus 1 cubed. So now we can find this answer, the answer to this, because this we're going to get it in what we're going to do, okay? I know I've taken time just explaining this because that's the hardest part. Everything else we do, you can do by yourself. Okay, so how do we get this? We just multiply both sides by pi over 8. Okay, so let me erase this. This will be equal to, this is pi over 2 times pi over 2. That's pi squared over 4. So we can have this to be pi squared over 4 multiplied by pi over 8. So the answer is pi cubed over 32. Okay, so this sum is pi cubed over 32. Welcome to regular calculus. So what we have here is this. I don't like saying natural log of x because I don't know what to do with it because I can't integrate it. But we can get rid of it. So all we have to say is, let's say let u be equal to ln of x. What does that mean? It means if you try to get rid of natural log of x, it means e to the u will be equal to x. Let's differentiate. If we differentiate this, we're going to have du will be equal to 1 over x dx. And what does that mean? That simply means that dx, because we need to replace this guy, it means that dx will be equal to x times du. But we said x is e to the u, so it's going to be e to the u du. That's what we have. Is there any replacement we need to do? Oh, we need to evaluate the boundaries. Let's change them. So let's do this. When u is evaluated, when x equals 0, as x approaches 0, u is going to go to negative infinity. And as as x goes to infinity, u is going to go to infinity too. Okay, so we don't really need to write that. So we're going to go from negative infinity to infinity of, this is now natural log of it, which is u squared divided by, this is going to be, what did we say x was? E to the u. So this is going to be 1 plus e to the u squared, which is e to the 2u. And what did we say dx was? Dx is this guy, e to the u du. Okay. Okay, now, if you look very well at this, if you want to know if a function is even or odd, just replace the u, the variable, with the negative, minus u, and see if you get the same thing. And I tried it, I got the same thing, okay? If you plug in negative u everywhere you see u, you'll end up with the same function after you simplify. So, because I know this is an even function, which means it is symmetric about the y-axis, I can fold the two together and just double it. So what I'm going to do is double this function, 2, so this is equal to twice going from 0 to infinity of, what do I have here? It's now going to be u squared e to the u over 1 plus e to the 2u du. Okay, and that's what we've got there. So what is left for us to do? We need to be able to integrate this. The problem is I tried integration by parts many times. I just kept going in a circle. So I knew integration by parts was not going to work. Okay, it worked at some point, but then it became very crazy. And I said, no, I'm not going that direction. So I decided to say, what if we express something as a series? For example, you have to know that it's going to converge. The way this is, it is not certain that this is going to converge. Remember, this goes to infinity, and this is from 0. Now, 0 is no longer a problem since we've done this adjustment. The major problem is the infinity thing, because I can plug in 0 for u here, and I'm not going to have a problem. Where I'm going to have a problem is this, okay? So, as this thing goes to infinity, there just has to be some kind of convergence. And the only way you can show that convergence happens is if you know that something is decreasing. Okay? When something is decreasing, then it's easy to show convergence. So if I look at this, I don't see convergence. Okay? Because even if I want to treat these as a power series, e to the 2u is not less than 1. But if I can make this negative, then it will be less than 1. E to the 2u is not, remember, you can generate the power series for anything that looks like this, 1 plus x. But this x must have its absolute value less than 1. Actually, 1 minus x, standard. Okay? But this must have the absolute value less than 1. It must cause things to go smaller and smaller. But if you look closely at this, nothing is getting smaller. Okay? And because it's not getting smaller, I want to make things smaller. So it's a lot of manipulation. So see what we're going to do. We're going to say that 1 over, let's add this, 1 over e to the 2u, we're going to try to make it smaller by doing this, by multiplying this by e to the negative 2u, and also multiplying the top by e to the negative 2u. And remember, what we had on top here was u squared e to the u. So by doing this multiplication, see what happens. We're going to end up with u squared. This times this is going to be u minus 2u. That's e to the negative u. You see this guy? I know how to integrate. Okay, this is easy to integrate. Integration by parts, you'll be done in no time. This guy, this multiplying this will give us e to the negative 2u, and this multiplying this will give us plus 1. So we have successfully, we can write this now as equal to 2 times the integral from 0 to infinity. Whatever we did has not altered this. It wasn't a u substitution. Now what we have here is going to be u squared e to the negative u divided by 1 plus e to the negative 2u du. This is beautiful because then we can work this into this. Before we move on, just look at what happens whenever you do a power series. I'm going to leave the link in the description to all the power series videos I've done. Some of them get very weird, but you can follow, okay? The power series, so this is going to be the same thing as 2 times the integral from 0 to infinity of, this is going to be u squared e to the negative u times 1 over 1 plus e to the negative 2u. Now, I know I can generate a power series for this because this is like the infinite sum of a geometric series. Because, see, the common ratio is this guy. And if the common ratio is less than 1, it will always converge. This is less than 1. Okay? The common ratio is less, and this is where the common ratio is, the absolute value of the common ratio rather. So we're going to do an analogy. 1 over 1 minus x is the same thing as the sum from n equals 0 to infinity of the common ratio x raised to power k. That's it. So if we look this way, what do we see? We're going to say 1 over 1. Oh, it's plus, but we have to change it to minus. So it will be minus minus, okay? Because this was plus. And this is going to be e to the negative 2u will now be raised to power. Are we using k? I want to use n actually. Oh, I used n. Yeah, n. So what do we have? It's going to be the sum from n equals 0 to infinity of, this is our x, this is replacing x, so it's going to be negative e to the negative 2u raised to power n. But if you look closely at this, we can break this up into negative 1. This is the same thing as the sum from n equals 0 to infinity of, this is negative 1 raised to power n, e to the negative 2u raised to power n. Nice. And that's it. So this is where the negative 1 raised to power n came from that we were trying to deal with here. And now this, we can still go back and combine with the rest. So see what's going to happen. This is the same thing as 2 times the integral from 0 to infinity of u squared e to the negative u multiplied by this sum. And this sum is this. From n equals 0 to infinity of negative 1 raised to power n e to the, I'm going to multiply this out, negative 2n. You see, if we multiply this, go in here, we're going to have e to the negative u times e to the negative 2nu. Well, we end up with e to the negative u minus 2nu, which is the same thing as what's common to everybody, negative u. So we can have e to the negative u, but left will be 1 plus 2n. Okay? So it means we can write this, see what has happened. I think it's cleaner now. So we can have this to be the integral from 0 to infinity of, this 2 is here, we still have our 2, and then we have now u squared. Then you have the sum here, which is going to be this. Oh, negative 1. Hey, we can't forget negative 1 to the n. And then we have e to the negative u times 2n plus 1. Let me write it that way. And then we have du. Okay, it's getting shorter. Let's do some smart substitution. Let's replace this with t. You see how beautiful it's going to turn out. So let's say let t be equal to u times 2n plus 1. So what do we have? It means that dt, if you take the integral of both sides, is going to be, well, it's going to be just this guy. Du will be equal to 2n plus 1 du. So that we can replace du with dt over 2n plus 1, right? So we can say that du is equal to 1 over 2n plus 1 dt. That's it. We're about to transform the face of this universe. Now see what happens. With this substitution, we can come here and say this is equal to, wait, the substitution we made, would it change our boundaries? Let's see. As when u is 0, well, t is going to be 0. And when u is infinity or goes to infinity, well, t2 will go to infinity. So nothing has changed. So we can say this is the integral from 0 to infinity of u. What is u now? We gotta replace u. What did we say u was? We didn't isolate u. Hey, u is t over 2n plus 1. Let's write that too. U equals t over 2n plus 1. Okay? So now we're gonna write this as t over 2n plus 1 squared. Let's just do it this way. Okay, so that's our u squared. And then we're going to have this sum. We're doing all kinds of replacement. Now this is going to be, we still have our negative 1 to the n. And e to the negative u will become e to the negative t. And our du is now, this is going to be times 1 over 2n plus 1 dt. Okay, it looks a bit messy, but just look at what we've done. You see this guy and this guy can be together, or we can move this guy here. And since we're now integrating with respect to t, anything that does not contain t can go all the way to the back. So this guy times this will become 2n plus 1 cubed. Our negative 1 to the n is going to be there. And what is left is just this times this, which I told you from the beginning, I know how to integrate and you know how to integrate. And we're almost at our answer. Copied and pasted. Now let's get rid of all the things that are not important. So watch this. This guy and this guy can be together and be happy. And I know that I can multiply this by this. So what I have essentially, okay, just so you know, I'm going to move this, compress them, and then separate the things that I need to be in the integral and the things that I don't need to be in the integral. So what I'm going to have will be this. I'm going to have 2 times the integral from 0 to infinity. Let's put this here because it doesn't matter. Okay, n equals 0. And what I have here is infinity. So if I multiply this by this, I'm going to end up with 1 over, so I'm going to end up with this negative 1 to the n over 2n plus 1 cubed. And then I'm going to have t squared multiplying this. So I have t squared e to the negative t dt. Let's go. Let's go. So watch what happens. Everything here has nothing to do with dt. So I can take it outside. But remember that this is a sum. So I can just take this and take it to behind the integral sign. Why can I do that? Because I know that this converges. Remember, look, the bottom is getting bigger and bigger. The top is just there. And we already showed that when we obtained the formula in the first place. So this is convergent. And I also know that this is convergent because I know I can integrate it and I can find the answer. I already know. So this is not the ideal method actually of getting this. You could have done it in a shorter way. But see, I like showing all the skills you can apply whenever you're taking or doing any calculus problem, especially integration. It's an art, don't forget. So here we go. I'm going to rewrite this to be equal to, I'm going to move this. So this is 2 multiplied by the sum from n equals 0 to infinity of -1 over 2n plus 1 cubed, or -1 to the n, multiplied by the integral from 0 to infinity of t squared e to the -t dt. We already know the answer to this, right? I'm just going to write it. There's going to be 2 times, this answer is pi cubed over 32. Pi cubed over 32 times this integral. Join me as we celebrate the DI method. Now, remember that this is an improper integral, which means you can't plug in infinity after you're done when you're evaluating. So you're supposed to take limits. So this limit is supposed to be, this integral actually is supposed to be rewritten. So we're supposed to do this. It is the integral from 0 to infinity of t squared e to the -t dt actually should be written as the limit as, let me pick the letter R, the limit as r goes to infinity of the integral from 0 to r of t squared e to the -t dt. This is the beautiful way to write this problem. But let's assume we've written it this way, okay? Let's do DI method. Differentiate, integrate. What would you like to differentiate? Always the polynomial. Okay, so we got t squared, not always, but in this case, polynomial and e to something, you should do that. And this should be e to the -t. So if I differentiate this, I get 2t. One more differentiation, I get 2. One more differentiation, I get 0. And I stop. And I put my plus, minus, plus, minus. And when I go to the other side, this is just -e to the -t. This is just e to the -t. -e to the -t. And how do you record your answers? This way. And because there's a 0 here, you're done. Because this time 0 will be 0. The integral of 0 is 0. So you stop. So our answer here times the limit as r goes to infinity of, this is t squared times, and that's going to be, oh, it's going to be -t squared over e to the t. That's the first one. This is going to go to 0 ultimately because e to the t gets bigger faster than this. So for all the time that r is going to go to infinity when you evaluate ultimately, yeah, we're going to get there. Don't worry. So this is the limit, and the other point is going to be negative times positive. So it's going to be minus 2t over e to the t. And this is going to be minus, is it minus? Oh, it's plus. Oh, it's minus. Minus 2 over e to the t. Okay, so this is what we need to evaluate from 0 to r. Equal to pi cubed over 16 multiplied by, for this case, what do you have? When you plug in r, or not plug in r, as r goes to infinity, each of these will go to 0. Clearly will go to 0. So I'm just going to put a giant 0 and say minus. When we plug in 0, what's going to happen? If you plug in 0 here, there's going to be 0 over whatever this is, 0 over 1, which is 0. Okay? If you plug in 0 here, it's the same thing, it's going to be 0. But when you plug in 0 to the final one, what you get is this is going to be 2 over 1, but negative, minus negative 2 over 1. So your answer is pi cubed over 16 times, Yeah, times 2, because this is positive 2. Times 2 over 1, which is pi cubed over 8. And this is all we've been working for all day long. I hope you picked up 1 or 2 skills in this video. Never stop learning. Those who stop learning, stop living. Bye-bye.